less than 1 hour to go. So what I'm going to do is I'm going to go briefly about the hydraulic conveying. And thus, this will be much easier for us to start with doing too much examples next week instead of spending the time explaining this system. So, do you know what the definition of slurry material? Oh, this one is working. Sorry, just give me 1 second. Do you know what the definition of the slurry material? Now, if I'm going to have a lump, okay, a rock, this will be solid. If I'm going to crush it, it's going to be powder, right? If I'm going to have water, it's liquid. If I'm going to have methane, it's gas. If I'm going to mix a water with powder, we call the suspension a slurry material. So actually the mud is a slurry material. Okay, so now, do you know the meaning of the slurry material? If you know, just raise your hand if you were listening. Okay. So now the slurry material is a mixture of powder and liquid. We mix them together so it can be easier for us to pump the powder and then separate it from the liquid. So it's something like what we've done when we mix it with the air and then separate them. Usually for the sand and for the ash material, we can mix it with the water, make a slurry, which of course is going to have a specific gravity more than the water, more than 1. We put it in centrifugal pump and pump it through the pipes till the end location, and then we're going to separate the water from the ash and reuse the water and accumulate the ash at the dumping area. That's just an example. So let's have a look about the technology in general, hydraulic conveying, or what we call the slurry pumping. So we said that in this case, we're going to mix the solid matter with the liquid carrier and then form the slurry. It's a mixture of liquid and the solid particles. The particles can be large or it can be small, according to the characteristics of this material. Then we're going to have the slurry transport by the gravity flow in the films, which has been used for many years. They mix it somewhere at the top of the hull and then using the gravity to drain the water to the bottom, and then they're going to separate them. I think that you saw many of the Western movies when they had the gold mine, and actually they had open channel. They mixing the material they're taken from the mine, and then they start to run it through water channels. And at the end, they're going to start to separate the gold from the sand from the water and get the gold. That's a very common thing. Short distance hydraulic convey using the slurry pumps has been developed during the 20th century. They start to pump the material for hundreds of meters. And later, they start to have long distance pipelines, slurry transport were introduced. They can pump the material for over hundreds of kilometers. And that's actually available everywhere in Australia. For example, they built something for the power plant, which burning the coal, and they had a problem with the recycling of the ash. So they start to actually pump it to hundreds of kilometers away in the desert, and they start to dump it there. So these are the centrifugal pumps we are using for this operation. You can see the size of the human worker in comparison with the size of the pump. So of course, this tells you that the larger pump it's going to have a higher flow rate for the material, but not necessarily it's going to have a higher pressure for the head. Once again, definition of the slurry is a mixture of the virtually any liquid combined with some solid particles. The combination of the type, size, shape, and quantity of the particles together with the nature of the transporting liquid will determine the exact characteristics of the flow properties of the slurry. Sometimes they're using just water, but sometimes the water may be activated with this material and causing the rust. They're using the kerosene in these cases. I know the kerosene actually can be ignited, but they have to work with it because there's no other option. The slurries can be broadly divided into two general groups. The first one is going to be non-settling, and we can have the settling types. In the settling types, the material will running at the lower half. Non-settling is going to be fully mixed, something like the diluted type of the airflow in the pneumatic system. Non-settling slurry entail very fine particles, which can be form a stable homogeneous mixture, exhibiting increase the apparent viscosity. And these slurry usually going to have a low wearing properties, but require a very careful concentration when selecting the correct pump, and they dry because they often do not behave in the manner of normal liquids. It's going to work something like what we call the non-Newtonian liquids. When the fine salts are going to be present in the slurry in sufficient quantity to cause this change in behavior away from the normal liquid, they will refer to be a non-Newtonian liquids. On the other side, the settling slurries are going to be formed by the coarser particles and tend to form the unstable mixture, which were the coarser particle will start to settle at the bottom. And also it's going to give you a very wearing effect because the coarse shape of the material. The type of the slurry also referred to being a heterogeneous type. So the slurry pumping is a long number of different pump types used in the pumping of the slurries. We usually have the positive displacement and special effect types as the Venturi ejectors once again, which used, but far most common type is going to be the slurry pump. It's going to be the centrifugal pump because it's easiest to manufacture, easiest to maintain, and also can send the material for the most flow rate using the less power. So, yeah, we mentioned that centrifugal pump is going to generate centrifugal force by rotating the impeller and to impart the energy of the slurry in the same manner as we have in the clear liquid type centrifugal pumps. That will be the only similarity between the water liquid centrifugal pumps and the slurry centrifugal pumps. I don't want to explain that a lot, so I'm going to just jump to the topic directly. This will be different types of the pumps we have for our slurry pumping. We have the horizontal pumps, which is going to be the line. That means it's going to take the liquid from the line side and send it vertically. Usually, we're going to have the features of the casing linears and the impellers of the customers for hard metal materials is going to be combined, used to make the pump. We can have the inline type, and in that case, we're going to have it from the same direction. The screw of the pump features metal casing with no separate linears or no elastomers wheel parts. We can have the vertical pumps like the submersible pumps. Actually, it's going because this part is going to be submersible within the liquid, and the motor is going to be at the top. It's going to have the impeller here, generate the pressure that push the material and feeding the system. This one usually is going to have the less efficiency among all the other types. We have the type AF, and this one is going to take the materials from the vertical direction and send it to a horizontal direction. It's going to have type of the cyclone to increase the efficiency of the pump. The jet pumps using the same effect as we explained with the pneumatic system. We're going to have very high stream of the liquid coming through the jet and then mixing with the soil material. And we're going to send the slurry at very high velocity through the conveying pipes. Now, the components of the slurry pump are going to be very simple. The most important thing is going to be the impeller, which is going to change the kinetic rotation of the impeller to an energy to move the slurry in the pipes. We can have different pipes of the impellers. You can see that we are going to have the covered type and we have the open type. Also, we can have the back struts open or closed, depending on the thickness of them, and this will affect a lot on the transferring of the energy from the pumps to the liquid. Okay, so I don't want to go through that, just leave it for the reading. The most important thing for me is going to be the calculation type. So once again, this is the open impeller type, and this will be the closed one. This one can generate higher pressure inside the impeller, and thus it can send the material, the slurry, to a higher head of pumping. And I guess that you remember what the term head is. That's mean, well, actually, we consider that as the elevation. But this will usually again to translate it into a distance that we can send the liquid to. You will see through the calculation, what we usually going to do is we're going to consider what will be the equivalent height for a certain distance or shape of the pipe and to be added as a pressure head for our design procedure. I think once again, you learn that from your fluid dynamics subject. Okay, so usually most of the impellers are going to be a closed type, as we mentioned earlier, with the front struts going to be available for them, but open type impellers also sometimes can be used for special applications. Well, I'm going to, well, I just mentioned that. We said that the closed type is going to have higher efficiencies, are going to have also less prone to wear in the front linear region. The open impellers are going to be most common in smaller pumps or where the particles blockage may be a problem, or where the shear provided also going to be an open impeller is going to be an 8 for the pumping port. Now, of course, for the impellers, we are going to need the casing. Otherwise, we're not going to move any material. Most of the cases are going to be slower than their water pump cousins, and primarily to reduce the wear through the lower internal velocities. Okay. Usually, it's going to have the semi-vulture or the annual geometry for the casing, and these differences are going to be illustrated in the figure on the next page. The efficiency of the more open casing are going to be less than that of the bullet type, because it's going to have closer casing to the impellers. And these are the different types of the casing. So you can see for the bullet, we are going to have a closed, the narrow area here, and this will cause higher pressure to be generated, and thus we're going to have better efficiency. This is the semi-full bullet, and this will be the constrictive type, and this one is going to have less efficiency, but it's going to have less effect to the wearing material. Now, the range of the application we have for the slurry pumps is going to be quite wide, and some of them, well, mainly they're going to be used in the mining sector, because usually what we do in the mining, we send the water that's going to cool the equipment down there and do the excavation process. It's much easier, and thus we can mix the material, whatever we're going to do in the mining material with the liquid and start to pump it outside. Because if you ever seen how the mining get to be done, not the coal mining, general the metal mining is going to be in the mountain or in the under the ground. So you're going to have a set, very complicated tunnels inside. So the only way to move the material outside is going to be by mixing it with the water and pump it outside. Slurry pumps are also going to be widely used for the disposal of the ash from the thermal power plants, and this is the most common application we have it in New South Wales, at least, because the for the mining of the metals is usually going to be done in New South Wales. It's going to be Queensland or Southern Australia, so sorry, and Western Australia. So in New South Wales, mostly, and Victoria, mostly it's going to be used for the ash disposal from the thermal power plants. Other areas where the slurry pumps are going to be used will include the manufacture of fertilizers, the land reclamations, the mining by the dredge, and the long distance transportation of the coal and the minerals. Now we still have increasing global focus on the environmental and the energy constraint will certainly generate much wider uses for the slurry pumping in the years to come. Now, the concept of the material selection of the materials to be used for the slurry pumping application is not going to be a previous procedure. We're not going to have a universal material for all the pumps for all the application, mainly because we are going to have the weighing effect. More materials going to be sensitive to other materials, and also we're going to have the effects of the chemical reaction. The procedure must first account for all factors, which are the variable characteristics of the particular slurry. The procedure must take into account the constraint imposed by the following: what the type of the pump we are using, what will be the pump speed, and what will be the option within the range of the models available. The basic data required to make selection of the type of the material for the pumps is going to be the particle sizing of the solid to be pumped, the shape and the hardness of the solids, and the corrosive properties of the liquid components of the slurry to be pumped. Now, if I'm going to use, for example, the cast iron, maybe some of the materials going to be more reactive to with the cast iron, damage it very fast. Sometimes we need to use gray cast iron, for example, which is going to give it more properties and longer time and more resistance. The material selection of the pump linears and the impellers made for two basic types of the materials. You can use elastomers, and this should have a wear erosion resistance cast alloy. The elastomers, you know what the elastomers is. It's type of the polymers, and the most three elastomers commonly used types are going to be the natural rubber, because it's going to be very good extrusion resistance for linears, but it's going to be limited to the particle size of 5 millimeter in size for the impellers. May not be suitable for very sharp edges because it can be weighed very fast, may be damaged by the oversized solids or trash. The impeller preferable speed should be less than 27.5 meters per second. Also, it's going to be damaged very fast due to the high temperature. So we need to avoid having the thermal breakdown of the linear. Unsuitable for the oil, solvent, or strong acids, and unsuitable for the temperature if it's going to be passing 77 degrees. As alternative and more advanced linear, we can use the polyethylene. Used for pump side linears, preferable speed of the impeller is going to be higher than 27.5 meters per second. So if we're not going to be able to use it with the rubber, natural rubber, we can use it for polyethylene. The erosion resistance is going to be greater because, of course, it's going to be harder material. Has less erosion resistance to the fine solids than the natural rubbers, but has a greater erosion resistance to the coarse, sharp edges particles than the natural rubber. It's going to be unsuitable for the temperature exceeding 70 degrees. So let's see what will be the case if we're going to have more than this temperature. Also, it's not suitable for concentrated acids and alkalis like the ketones and esters, the chlorinated, and the hydrocarbons. So here comes the role of the synthetic elastomers, which is going to be a mixture of multiple elastomers. So they are used in special chemical application under the following condition. not as erosion resistant as natural rubber. First, have a greater chemical resistance than the natural rubber or the polyethylene. Generally allows for the higher operating temperature than the natural rubber and the polyethylene. Now, for the material, we can use the wear erosion resistant cast alloys, and this is going to be special cast alloys that can take more resistance for the what they call it. It's not. It's have a certain name. Anyway, it's going to have more resistance than the usual types of the cast iron against the coarse or sharp edges particles wearing effect. Also, it can operating at very high velocities and high operating temperatures. Now, we need to define the application and the constraints we have for our application. The most properties of the slurry we can have is going to be the abrasion. If I get to have a particle with irregular shape and quite larger size, usually with the mixture movement of the slurry attached to the wall is going to cause what we call the abrasive action. So it's going to work like a grinder. It's going to start to damaging the wall due to the high friction. So we're going to see the next figure. It's a three major type of the abrasion, where it's going to be the gouging, which is going to be the best one, just touching the things. Or we can have high stress grinding and the low stress grinding. In centrifugal slurry pumps, the abrasion is only going to be occurs in two areas. First, between the rotating impellers and the stationary throat push, and in between the rotating shaft sleeves and the stationary packing. So once again, the gouging is going to be almost the best effect because it's hardly touching the things. It's not going to damage the work. Larger particles are going to have stress impact, for example, the jaw and the gyratory crusher, but it's going to break up itself. The smaller one is going to have high stress grinding. And in this case, smaller particles are going to have high stress sliding effects like the ball and the roll mills. The small particles and going to have a small stress, low stress, like the screens and the tubes. So the three types is going to have a different types of the wear. The more dangerous one is going to be the lower one, especially if it's going to have an irregular shape. The other effect is going to be the erosion. Now, the erosion is not going to be the effect of the damage of the material due to the hard particles, but this one is going to be done due to the wear of the loss of the surface material by the action of the particle entering in the fluid itself. So the liquid itself, with high friction with the walls, is going to start to erode the material. Erosion involves the transfer of the kinetic energy of the particles, which does not occur in the abrasion, and transfer of the kinetic energy from the particle to the surface will result in very high contact stresses, while the overall contact pressure at each impact site is going to be small. Specific contact pressure is going to be high. So it's something like, again, to use the case of the abrasive jet cutting or the jet cutter. So the high kinetic energy we are going to have in the liquid particles is going to cause the erosion of the material. The same thing actually happening inside the pipes and inside the pumps during the high velocity pumping of the material. So that's what will happen actually in the case the three basic types of erosion. We're going to have either the sliding bed, we can have a random impact, and we can have a directional impact. The pump impellers, the slide linears, and the volts were due to the quite different mechanism as follows. First, the pump impellers are going to be subjected to the combination of the direct impingance and sliding bed wear, and the low angle of the impingance is going to cause the damage. Second, we are going to have the slide linears are going to be mainly subjected to the sliding bed wear and some of the low angle impingance. And the volts are going to be subject to direct impingance on the cut water and the sliding bed erosion around the periphery. Now, the other effect is going to be the corrosion, and this one is going to be unlike the abrasiveness and the erosion. The corrosion is a chemical reaction. The corrosion of the metals involve the flow of the electrical current. Since the deterioration depends on the electrical factors as well as chemical factors, it's going to be extremely complex phenomena. The basis of the corrosion processes is going to be the one electron is going to be missed from the freon. And that's actually the Fe3 is going to be what we call the rust. And so I don't need to read that because just chemical. The most important thing that is going to, that due to the electricity effects, we're going to have those of the electrons, and then we're going to have the Fe3 instead of the Fe. Many different types of the corrosion, some of which are going to be uniform, galvanic, crevice, the pitting types, the intergranules, the selective leaching, and we have the stress and the erosion of corrosion. The later one is going to be the most important one in the case of slurry application, because the two effects of the erosion and the corrosion work together, and are going to often going to be difficult to identify separately. Now, one other problem we have is going to be the solid concentration, where we're going to have the adverse effects on the pump performance caused by the solids in the slurry, compared with the pump performance when the pump clear water. And principally, it's going to be due to first slip between the fluid and the solid particles during the acceleration and the deacceleration of the slurry while entering and leaving the ampullus. And also, we're going to have an increased friction losses in the pump, and these losses will increase with the density of the slurry. So higher slurry density is going to have more friction losses in that pump. This figure actually is going to be a relationship between first the CW, which is the concentration of the solid in the slurry by weight. For example, how much kilogram of material we have per kilogram of water. The average particle size is shown in the x-axis below. And here is going to be the specific gravity of the solid. That means the density of the liquid, of the slurry material, of the solid material, with reference to the density of the water. So how to use this chart? If I know the value for the specific gravity of the solid, and this can be very simple. For example, I'm using the sand to be the mixture with the water to make the slurry. So the sand have 2.65 as the value for the specific gravity. Let's consider that the particle size, the average particle size of this sand is going to be equal to 9 millimeters. So I'm going to make a straight line from the 9, okay, intersected with 2.65 line here for the specific gravity. Now I'm going to move horizontally and intersect with the CW, which is the how much kilogram of sand we have in the total mass of the slurry. Let's say it's going to be equal to 25%. So I'm moving until I'm going to intersect with the 25% line, which is going to be that one. That's 25%. Okay, so once again, 9, intersect with the 2.65, move horizontally until I get to intersect with the 25%. Now, when I got that, I just make another line straight upward, and this will give me the HR and the ER. The HR is the percentage between of the head of the slurry divided by the head on the water, and the ER is the efficiency of the slurry over the efficiency of the water. Usually, both values are going to be the same. So I got something of 0.86, for example, as a percentage, or 86%. We're going to use this chart a lot in our calculation procedure for the Warman pump type. Now, effects on the material selection, the property of the slurry, of course, is going to have a direct relationship to the type of the material we're going to use for the components within the slurry pump. I don't want to use the pump for a certain material, then it's going to be out of service within a few months. So I need to select the pump after study all the characteristics of this material and its possible and potential effects on the material of the pump I'm going to select. Now we have an important calculation for the volume of the flow rate. Usually the volume of the slurry to be transported must be reliably determined before defining the slurry pumping application. So without a clear understanding of the volumetric requirement of the pumping, I can note this design or select the pump size and type. So for slurry pumping, we need to know the following factors. First, what will be the solid specific gravity? Also, I need to find what will be the total tonnage of the solid required to be pumped, and the concentration of this solid within the slurry mixture. So the SG, the massive flow rate, and the CW, or the concentration of the solid in the liquid mixture. These three factors will need to be determined prior to selecting of any slurry pumping. How you can decide that? You have to check what is the material, what is the requirement of the process. For example, if you're going to have thermal power plant, you have to know how much ash is going to be generated every hour. And the concentration of this solid within the slurry mixture, depending on the type of the pump you have, what will be the best mixture that can be pumped efficiently without any damaging for the pump material. The pipeline length is always going to be important in any fluid dynamic design, because longer pipe is going to have more friction with the wall and the material, and thus we're going to have higher pressure loss, and thus we're going to need a bigger pump pipe to work. Yeah, so the longer pipeline is going to be greater friction force to be overcome by the static pump, and then the pump should need to be larger. So once again, before we're going to select the pump, we need to know what will be the length of the pipeline we're going to have. Now the pump pipe length are going to be divided into the actual length and the equivalent length. Because if we're going to have a bands or we're going to have the elbows, these elbows have equivalent length, which is going to be depending on the diameter and the angle of the bending. So we need to do something called the static head requirements. Okay, static head is going to be the actual virtual height. So if I'm going to pump from the bottom of the valley to the head of the mountain, for example, or the hill, I'm going to have the height of 150 meters. So this will be the static head required, the actual vertical height, over which the slurry is going to be lifted, must also be accurately determined prior to the pump selection. This will be the easiest one because it's going to be in a flat situation where the vertical heights involved can be measured or obtained from the drawings. In the case of the overland pipelines, they are going to have surveying data, so it's going to be required to obtain this vertical information. Now, we may have variation in the vertical height, and in that case, we may have multiple centrifugal pumps in multiple stations. Okay. Now, the pipe size, which means the diameter. Now, usually we have standard diameters for the pipes, and you have to remember that when you do a design procedure for piping system, you always need to use the standard types. I mean, if we have the 4 inches, 5 inches, 6 inches, you have to make your design to be suitable with these diameters. Now, what the problem we have if we're going to use a smaller diameter pipe? What will be the problem we have with the small diameter pipes?
Less mass flow.
Less massive flow and higher velocity.
Higher velocity.
Yeah. And it's going to be the opposite. If we're going to have larger diameter, we're going to have less velocity, higher massive flow. Now, mainly because the massive flow is a relationship between the velocity multiplied by the area. But usually, the smaller one is going to have throttling effect, and thus we're going to have higher velocity, but the area is small, so we're going to have less flow rate. Usually, the high velocity is not going to be something desirable because it's going to increase diffraction. So we have to select the optimum pipe diameter. Doesn't have to be too small, doesn't have to be too large. We need to make multiple calculations, or actually we have one equation which is going to be an indicator if this pipe is going to be required, acceptable for our design or not. So use of the pipe is going to be too small, resulting in either insufficient flow rate or excessively high power requirement. By way of the example, a typical slurry flow rate of say 100 liters per second pumped over 1,000 meter will generate a fraction of 1,253 meters in the 100 millimeter internal diameter pipe versus only 60 meters in the 150 millimeter internal diameter pipe. So just imagine, I'm just increasing the diameter by 2 inches. So taking from 4 inches of 100 millimeter to the 6 inches, are going to reduce the friction height by the value of how much? 200 times. By 200 times. Theoretical power consumption will be around 2,000 kilowatts for the 100 millimeter pipes compared to the 250 kilowatts only for the 150 millimeter pipes. Now, once again, the velocity at which this slurry is going to be pumped within the pipeline must also be evaluated to ensure the sufficient velocity will be available to maintain the solids in the suspension. So I don't want to have the velocity to be too slow because in that case, the material will be settled down and thus it's not going to be moved along the pipe. So at the end of the pipe, I'm only going to get the water, but the material has been built up inside the pipe. So insufficient velocity is going to be available. So the insufficient velocity is going to be available. The solid particle will be progressively settled within the pipe and ultimately causing the total cloggage of the pipe. Now we have something called the pump performance graphs, and I don't know if you used this one earlier in any subject. I don't remember that we have any subject that you should know how to use that. But in real life, you cannot select the pipe without knowing how to read the pump performance graphs. So to understand the performance of centrifugal pump, it's necessary to understand how to perform and how the performance of the individual pumps are going to be determined and presented. Centrifugal slurry performance is usually going to be presented in the form of the performance graph with the flow rate and the head being plotted for the constant speed. Every model, and actually every company, have their own performance test and have their own performance graphs. This is an example for typical pump test performance graph shown in this figure. So we're going to have the flow rate, and we are going to have the head on the y-axis. So the head is going to be with these points, and this one is going to be for the power required, and this line is going to be for the efficiency %. So for example, in the case of 25 liter per second, we can see that the head we can send the materials to is going to be equal to 32 meters. And the efficiency is going to be about 50%. And the power required to do this operation is going to be equal to 20 kilowatt. That's just an example, but of course we have more advanced shape for the pump performance graph like this one. Now this will be a typical pump performance graph. Once again, we're going to have the flow rate here. We're going to have the head on the y-axis. Now how we are going to use this one? Let's say that I'm going to have the 60 liter per minute. And the head required to be pumped is going to be 30 meters. Now I'm going to have the intersection of these 2 points at this location here. That means the efficiency is going to be almost 81%. Okay, and the value for the efficiency rate, efficiency was 81%, and the value for what we call it, number of the revolution per minute is going to be 1,600. It's good. The MPSH value, and we're going to explain that very soon, is going to be equal to 3.8 meters. That's 3. That's 4. So we're standing here at, it's going to be 4.5 meters. Okay, so that's how we can find the flow rate, the head, the efficiency, and the NPSH value and the RPM value. We're going to do that during our design example next week. It's going to be exactly similar to the quiz we're going to have. Now, system resistance curve also should be considered. The cases of the centrifugal pump do not allow for the fixed capacity output, but rather balance output against the pipe system. So this is an example for the head and the flow rate, and this will be a typical resistance curve, depending on how much percentage of the solid we have in the liquid. So this is the pure water. This is 20% of the slurry is solid, and this is against the 40% of the slurry is going to be solid. So you can see that at the same value, the head is going to be always, the required head solid is going to be higher when the slurry is going to contain more solid material, because simply it's going to be heavier. So the intersection of the pump performance curve and the pipe system resistance curve will determine the actual pump duty point at which the pump will be operated. Okay, so this will be the 2 lines. The intersection will give me what will be the actual pump duty high head pump of the process of the H value. So in general, the piping system we have for the slurry operation is going to be defined as all piping, fittings, and devices between the free surface liquid level at the bottom at the intake side to the point of the free discharge at the output end of the pipe. Centrifugal slurry pumps must be overcome both the static head and the system resistance to achieve the movement of the slurry to the output end of the pipe system. The friction losses always going to be occur in the pipes and the other components like for example, the expansion or the divergence or the elbows. It's always going to be calculated, and then it's going to be added as the equivalent length. The system resistance curve is going to be, in fact, the peculiar of any particular piping system and cannot change unless something in the pipe system is going to be changed. For example, the increasing or decreasing the length of the pipe, the varying in the diameter of the pipe, and the varying in the static head. This is head. The friction losses is usually going to be established for water, and then we're going to have a correction factor to account for the variation in the slurry concentration. We need to have the resistance curve to be determined when the evaluating of any slurry pumping application, and to enable the duty point and the potential flow rate, the variation to be assessed correctly. The systems graphs, such as the figure 9 and 10 we're going to see next, are going to be helpful in determining the effects of the altering pump speeds and or the altering some of the aspects of the pipe system, like this one. This will be the other graph. Usually, we're going to have the values of the heads, friction heads, are going to be variation with the value for the flow rate we are going to pump in this pump system. This will be an example actually. And first, we're going to have the steps of the selecting of the appropriate pump, and I'm going to leave this one for the next week, because next week we're going to focus on the calculation part. I consider myself, I covered the theoretical part, so I don't have to repeat this one to you later. As once again, just to summarize what we talked about in the last hour, is that we have something called the hydraulic or the slurry pumping. And this slurry pumping will mix the solid with the liquid, and then we get to have the slurry material that can be pumped using the centrifugal pump. At the end of the centrifugal pump, we're going to have a separation system, separate the solid from the water, reuse the water, and do whatever you want to do with the solid part. Well, it's going to be, once again, this can be an ash, which can be dumped, or it can be a mineral, which can be separated and used in processing. We said that the pumps are going to have different types. The most important one is going to be a centrifugal pump, and the pumps itself have different types of the impellers. We have the closed type, we have the open type. The closed type is going to be good to generate a good efficiency and higher pressure, but the open type is going to be useful if you get to have higher size of the particle for this slurry, because in the closed type, the material may stuck inside. Selecting of the material of the pump should be first, depending on the characteristics of the material we are pumping, depending on the size, depending on the chemicals, depending on the velocity, depending on the temperature. The other thing we learned here, that we need to use the most appropriate diameter for the pipe. It doesn't have to be too small, doesn't have to be too large. We need to do the calculation to find the optimized diameter of the pipe. Whatever we're going to have in the pipe, like for example, the changing in diameters, or we're going to have the expansion, that means the diameter is going to increase, or contraction, diameter is going to be reduced, the elbows, or the joining, we always need to calculate what will be the pressure drop and add that as an equivalent head. Also, we need to check what will be the static head, which is the actual elevation between the inlet and the outlet. After collecting all these parameters, we can calculate what will be the equivalent length of the pipe, and accordingly we can find what will be the head of the pump. We know the flow rate, and then we're going to calculate the other parameters like the RPM value, the power required, and the efficiency of the pump we are going to be selecting. Now, the steps to do this design procedure is going to be listed in the following pages. And once again, I'm going to leave that for the next lecture, so I don't want to have very long lecture today. And this, I know this will drive you boring, and I don't want you to do that. The other thing we learned today was the pneumatic conveying, which is how to use the air to convey a light material from for either processing or just for the material handling application. So I think this will be all for today, and again, so